complex manifold T such that T is in the epsilon neighborhood of the original point of the complex plane, and the second, x0 is the original given manifold, and number 3, so this infinitesimal deformation which is defined from linearized harmonic map of x to xt is equal to the given one. So linearize ft to get phi 0. So maybe I should say, given any compact complex manifold and a phi 0, which is the harmonic form in the tx value, the 0, 1 form, can we find a family such that this is true? So as I said, the differential equation, the partial differential equation I've just set up is something like this. Or more precisely, we need to find the following. We need to find phi, which is parameterized by t, where t is very small, such that the following is true. Number 1, this is equal to 0, which is the integrability condition. And number 2 is phi 0 is assumed to be 0 because in the so our d bar t is d bar minus phi t. So in that sense, when t is equal to 0, the d bar t is equal to d bar. And the number 3 is we wish that this is the given one, which is a 0, 1 valued T1, 1, 0 holomorphic tangent bundle valued 0, 1 form. So basically, if we can find a smooth family of compact complex manifold, which is called the deformation of the original manifold, is equivalent to solve this equation, to solve it for t small. Okay, so the classical way to solve such an equation is through the so-called power series method. We assume that this phi can be expanded as power series, convergent power series of t, and we put it in, then we try to solve it. But so this method can be formulated in the following way, which is basically Kronish's idea. So it is said that basically it's said that we don't know. In general, this equation may not have any solution. However, this equation will always have solution when t is small. So here here the notations are, phi t is always a 0, 1 t1 0 form. So the Lie bracket of phi t is an element, still an element of t0, 1 holomorphic tangent bundled 0, 2 form. Okay, so this G is the Green's operator on this, is the Green's operator for the Laplacian on this bundle, and the d bar star is just the dual of d bar. So we can always, so by Kronish, we can always solve this equation for t small. This is basically by power series method. And so when the solution of this is equal to the solution of that. So in general, it's not true. There are obstructions. But in the following 3 cases, there's no obstruction. So we will see that basically this phi, which can be represented, if there's a solution, then the Lie bracket of phi and phi has to be d bar coboundary, and therefore the harmonic part of phi bracket phi has to be 0. So this will be a necessary condition, but actually we can Kronish proved that this is sufficient. So using that sufficient condition, we have the following three cases. So when Z happens to be a Riemann surface, that was very classical. It was known by Riemann that the deformation is always unobstructed in the sense that the solution of the original PDE is the same thing as that. So this is not surprising because Riemann surface is dimension 1. So for any harmonic part, there's no no 0-2 form, basically, not even harmonic one. So there's no obstruction. And Kodela, Nielenberg, Spencer in 60s proved that if we assume that H2 of Z, Tz is equal to 0, then it's okay. There's no obstruction. Or in other words, when we assume that this cohomology group is 0, then this is always harmonic. This is always co-boundary. So it can be that means it can be removed. So the most interesting case probably is when Z is a Calabi-Yau manifold. Okay. So this is proved by Tian and heavily using the so-called Tian-Todorov lemma. So regardless of these details, the point is for Calabi-Yau manifold, this obstruction group may not be 0 at all. For example, for Calabi-Yau threefold, by Serre duality, we can prove that H2 is never 0. So if Z is a Calabi-Yau threefold, so then H2 ZTZ by the Serre duality would be equal to H1, because 3 minus 2 is 1. And so canonical boundary is trivial, and we dualize it, we get this. Okay. So this bundle, this cohomology group is never 0 because at least the Kähler form is in it. Okay. So that means for Calabi-Yau manifold, in general, this is not equal to 0. Nevertheless, even with the existence of obstruction, we are still able to manage to do it. The trick is we start with the Cronish's method. We can always solve, starting with Cronish's method, we can always solve the following equation. Phi t is equal to phi prime 0 t plus half of d bar star g phi t phi t. And we know, even this was known by Kronish, that even if we can always prove that this is the harmonic part of this is 0, then it solves the original equation. But there's a Tian-Todorov lemma which is more or less combinatorial, state that in fact this is true. So the Tian-Todorov lemma is too technical to write down, but there's one main result. Main consequence of this is that if we have two phi 1, phi 2 harmonic Tz valued 0, 1 form, then we can prove that their Lie bracket has to be d bar star coboundary. So this is a combinatorial result. And with that result, well, if this is d bar star coboundary, then the harmonic part of that has to be 0 by the Hodge decomposition theory. So these three cases are the only cases we know quite well that the deformation has no obstruction. There are a few other cases, but systematically, these are the three big classes. I don't know other big class of manifold with no with the deformation with no obstructed. Okay, so let's go to differential geometry after having a quick introduction of Kodela-Spencer theory. So let's define the Will-Peterson metric, which is again probably everybody well known this, but let me just show you the definition. So on any modular space, on any smooth part of the modular space, we can define the so-called Will-Peterson metric, or we call it L2 metric, in the following way. So I wrote it in terms of Calabi-Yau, but actually we can do for any modular space. So the idea is, so this is the modular space, and these are fibers. These are families of compact Kähler manifolds. And if we have any tangent vector on the modular space, the very good thing is, the very good implication of the Cordella-Spencer map is that any vector you can identify with the information on that fiber. Okay, so the Cordella-Spencer map basically say d dt you can map to a phi which is h1 z tz. So this is so if we I cheat a little bit. So if we assume that the modular space is smooth, and if we assume that the Cordella-Spencer map is a isomorphism, then with this so-called Cordella-Spencer map, we have an identification of the modular space, the tangent vector space of the modular space at point z to this h1 z tz. Okay, so very roughly speaking, this identification is a horizontal direction is equivalent somehow to the vertical direction. Okay, so but the implication of Cordella-Spencer map is more than that. It not only say this one, you go this direction, it can be identified with that. It also says that even you take any derivative or you take any high-order differential operator on the horizontal direction, you can always convert it to the vertical direction. Okay, so this idea is, so for example, in Walpole's computation of the curvature of the Teichmüller space. So basically, the Weil-Petersen metric is a metric on the modular space. But through some complicated computation, finally, the curvature is in terms of a complicated integration. The curvature at one point is in terms of the complicated integration on that on one fiber. Okay? So even you take the derivative of the curvature, you can manage to do it, to convert it to the vertical direction. So that's the full implication of the Cordella-Spencer map. Okay, what I want to say is, for Calabi-Yau manifold, well, the Weil-Petersen metric can be defined in this general way, but it's very, very special. It is almost unique in the Weil-Petersen geometry, and let me explain that. So assume that we have a polarized manifold, and assuming that x and y are an element of this cohomology group, and which we identify it with harmonic forms using Hodge theory. And once we identify them in terms of harmonic forms, I can define the L2 inner product on this finite dimensional vector space, and such a so using this way, and so such a the Hermitian inner product defined in this way, and when you, in terms of the Cordella-Spencer map, will naturally define a Hermitian metric on the modular space. Okay, and with such a identification, that the matrix space, the matrix defined on the modular space is called the Weil-Petersen metric, and the Weil-Petersen metric happens to be Kähler. Okay, so let's make a definition. So the differential geometry of the Weil-Petersen metric on Calabi-Yau modular space is called Weil-Petersen geometry. Okay, so we want to be able to tell the properties of the modular space through geometric analysis or through the study of the metric on the Calabi-Yau manifold. So this theory tells us that the Weil-Petersen metric on the modular space of Calabi-Yau manifold is completely different. It's very different from like modulus Weil-Petersen metric on the Teichmüller space. So assume that M is a Calabi-Yau modular space of a Calabi-Yau manifold Z, and we assume that omega is a holomorphic family of non-zero Okay, so let me explain. So we assume that X is a Calabi-Yau n-fold. So X is a Calabi-Yau n-fold, and by definition, its kx is trivial, is O. It is a trivial bundle, and by definition, on any x we can find a omega x, which is a n0 form, and moreover, such an n0 form is holomorphic and nowhere zero. So this follows from the definition of Calabi-Yau manifold. And when we regard X as one Calabi-Yau manifold as one point on the modular space, then for each modular space, each point on modular space, we have an n0 form. And so when X varies, then we have a family of n0 forms. And we can actually choose those n0 forms to be holomorphic with respect to the parameters on the modular space. Okay, so this is what I mean. Let omega be a holomorphic family of non-zero should be n0 forms. And then the Weil-Petersen metric, which is the L2 metric defined before, actually has a very, very simple formula. Omega is negative constant dd bar of log, that's omega wedge omega bar. So note that omega is an n0 form. Wedging it with a 0n form, we'll get nn form, which is, you can integrate it in terms against z. Okay, so this is not only a very simple formula, but also quite useful in the following sense. So recall that by our definition of the L2 metric, we have to say, okay, Z is a Calabi-Yau manifold, then we have to choose a Ricci-Flat metric. Okay, using the Ricci-Flat metric, we can produce the pointwise inner product and then integrate against the whole manifold. We get the L2 product. So this expression is explicitly depends on the Ricci-Flat metric. Okay, even though that by Yau's theorem we know that on any fixed polarization there's a unique Ricci-Flat metric, we cannot write them down. For example, even on K3 surface, we don't know how to write the Ricci-Flat metric explicitly. And somehow, it's very strange that this expression of the Weil-Petersen metric, which is equal to the previously defined, has nothing to do with the Ricci-Flat metric. So it's fairly easy, given a Calabi-Yau threefold, we can write out omega. We can write out the 3-0 form explicitly. Therefore, we are able to compute the curvature of this Weil-Petersen metric much easier than we do for example, the curvature of the Teichner space. Okay, so the Teichner space is one-dimensional, but it's much more difficult than to.
Some spectral meaning of that, because in the case of Teichner space, it's a bit either dependent on combustion or the new election there, or so it comes from the spectral theory somehow. And here it seems completely.
It's not from spectral theory, but it comes from Hodge theory, let's say. Yeah.
But there is no further behind
maybe we can. I will explain later. Just in terms of one way to say that is this expression is explicitly in terms of Hodge variation of Hodge's structure, because this omega is so when omega is a 3-0 form. When you take derivative, then it depends on the variation of Hodge structure. But even for Riemann surface, everything depends implicitly in terms of Hodge structure, but this is an explicit expression. Okay, so probably I can partially answer your question indirectly later. So one thing is that I said the curvature computation of omega is easier than the curvature computation of Teichner space because of this expression. So because it's easy to compute, then we can compute the derivative of derivative. We can take fourth derivative. This is the advantage of studying the Calabi-Yau modular space. For Teichner space, it's very difficult to study it. Well, the Ricci curvature is negative which can be used as a Kähler metric, but it's not easy to take the derivative of Ricci curvature. For Calabi-Yau, we can. So, so as I said, this is unique, and unique not only it's independent of the metric explicitly, and it is in terms of Hodge, variation of Hodge structure is explicit dependence of the variation of Hodge structure. Okay, so one way to see, one interpretation of this is that the Weil-Petersen metric is the curvature of the first Hodge bundle. So we start with any Calabi-Yau manifold. We can always have a one-dimensional vector space Hn0. So if we putting this onto a modular space where each Calabi-Yau manifold is represented by one point, so attach each point, we have a one-dimensional vector space. So if we put this vector space together, we will get a holomorphic line bundle. And so the natural Hermitian metric for this holomorphic line bundle is nothing but wedge, omega bar integration. This is a natural metric. And with such a metric, the curvature happens to be the Weil-Petersen metric, just like that. So this may be an interpretation. It's a curvature of the Hodge bundle Hn0 over the modular space. Okay. So we not only need the first Hodge bundle to help us, we also need basically all the Hodge bundles to do the job. So this is a picture. so this is actually the Calabi-Yau quintic projected to our three-dimensional space. So I don't know. It's this is from Wikipedia. It said the projection of this to our three-dimensional space, but actually it shows that it's a two-dimensional surface. But anyway, it's quite complicated even for the simplest Calabi-Yau threefold quintic. Okay, so this is such a nonlinear object to study. So one way to do it is go through study the Hodge cohomology groups, harmonic N0 form, harmonic PQ form, harmonic RS forms. So those are vector subspaces. And when the complex structure of this manifold changes, so those so-called Hodge flags also changes. But the other side is more linear to study. So study this is called the variation of Hodge structure. And for Calabi-Yau manifold, the map is an immersion, more or less, is an immersion. So the variation of Hodge structure should, by definition, catches all the information of the original Calabi-Yau manifold. Okay. All right. So we realized, realizing the above picture, we take the following. We do the following. So let's assume now that we have a Calabi-Yau threefold. And for Calabi-Yau threefold, we can define the following so-called Hodge bundles. The first bundle, F3, is H30, the space of all non-zero holomorphic 3-0 forms. And the F2 is 3-0 forms plus 2-1 forms. F1 is this, and F0 is that. Okay, so the reason we write that is we want to make sure that these bundles, each HPQ bundles are C infinitive bundles, but there's a natural way to make these F bundles to be holomorphic. And in particular, this F3 for Calabi-Yau manifold is a line bundle because this is one-dimensional. And F0 is a locally flat bundle because if you have a Hodge decomposition, you put all these together, you get a cohomology group which only depends on the topology of X. So this is a locally flat bundle. It won't change with the variation of the complex structure. Okay, so why these things are useful? So because we have the following called the Griffith's transversality. So if you take any section of Fk and you take derivatives, so one thing is all Fk are the subbundles of Fk minus 1. And the Griffith's transversality tells us that if you take derivatives, you basically, well, this is not very accurate. What I mean is, for any V on the tangent bundle of cohomology group, then this one belongs to that. Okay, so basically you take one derivative, it must be there. It won't just go. Everything should be in F0, but for the derivative of Fk, it at most goes to Fk minus 1. In particular, if you take derivative of a holomorphic 3-0 form, at most you will get a combination of 3-0 form plus 2-1 form. That's what Griffith's transversality tells us. Okay, so the next one is only works for Calabi-Yau threefold. It's a very beautiful characterization of the manifold. This was done by Bryant and Griffiths. So let's assume that we are working on Calabi-Yau threefold, and F3 is a line bundle, which is the subbundle of F0, which is a locally flat bundle. It's a constant bundle. Okay, so we can write because F3. So we do the following. We assume that the dimension of the modular space is equal to n. And because it's a Calabi-Yau threefold, this dimension of M is equal to the dimension of H21. Okay, so by the extension. And so F3 is sitting F0. But what is the rank of F0? F0, remember, is H30, H21, H12, and H03. So basically, the rank of F0 is the dimension of the H3 cohomology group, which is 1 plus n. 1 is for H30, H21, H12, and this one. It's 2n plus 2. Okay? And since F3 is a subbundle of this rank 2n plus 2 flat bundle, so we can write any section, holomorphic section, in terms of this. So basically, we normalize the first component of section to be 1, which is allowed. You can always divide it a constant, divide it a number. And then we use the next n holomorphic functions as coordinates. This can also be proved that you can, at least generically, you can do that. And we put a coefficient on that. And then we let the rest to be holomorphic functions of Z1 through Zn. Okay, let's see what the Griffiths transversality, the implication of Griffiths transversality on this. Okay, we define a natural quadratic form, basically just the phi wedge per side do the integration. So if and only if phi per side are 3 forms, then this integration makes sense. Okay, so if phi and per side are 3 forms, that means this quadratic forms has to be screw symmetric, which means that we can always write it in terms of this. Okay, that's okay. And then the Griffiths transversality tells us that this is 0. Oh, well, this is not Griffiths transversality, because Q of F3, F2, F3 composed of 3-0 forms, and F2 composed of 3-0 and 2, maybe 2-1 forms. But no matter what the forms are, their wedge will be 0 because the holomorphic part is always more than 4. Okay, so this is always equal to 0. Okay, this is not follows from Griffiths transversality. And so remember that we have omega written in terms of this elementary form, 1 square root of 2z1 square root 2 of zn, and f0 fn. Okay, so we can take a gradient of omega by taking the partial derivatives. So let's say take zk. So this one, you take derivative, you get 0. And here, the only non-zero form is in the case direction, because other derivatives are 0. And then you have df0 zk, dfn zk. Anyway, you can take derivative. But then, this is 0, so that means you take inner product of these two, you get 0. But the quadratic form Q, the matrix is already written down, so you can actually compute it. So if you use the fact that with respect to Q, this vector is perpendicular to that vector. The equation we get is this. And so we can prove that with this equation, we can easily prove that if you couple fk with dzk, you get one form. Such a one form has to be closed, and it has to be exact locally. And that means we can write fk, actually it should be, there's a coefficient, but anyway. You can write fk in terms of, there's a holomorphic function u such that it can be written as the derivative locally. These are all locally. So here's the important implication. This is the Kähler potential in terms of the Weil-Petersen metric. The Kähler potential can be written like this. Well, so let's go back to the original example I gave. It's not as easy as that the Kähler metric can be written as the image of the Hessian, the holomorphic Hessian of one function, but it's similar, or at least it's close. So we will see that when the Kähler potential can be written like this. So u is a holomorphic function, and this is coordinates. Ui is the du dzi. Then its curvature, or the curvature of curvature, has specific property. Okay. All right. So let's compute the curvature of the metric. Okay. So by a straightforward computation, we will see that the curvature Rijkl is going to be Gij is the Kähler metric, minus something like is a f, where Fijk is called the Yukawa coupling, which is Fijk has to be holomorphic. Okay, so if we compare this curvature with the original one, for special Kähler manifold, Rijkl is equal to Gmn bar Uikm Ujln bar. So you will see that, well, the original one actually is there's a negative sign. You will see that there's an extra term. So that makes it different from the original special Kähler manifold. If a Kähler manifold with such a curvature expression in terms of Dan Fried and Strominger, it is called the projective special Kähler manifold. So when you take the derivative of, well, of course you can take the Laplace of its scalar curvature, but you won't produce too much. But when you take, but basically if you take the derivative, second derivative of this curvature tensor, then you will get something, just like you will get from special Kähler manifold. Okay, so this curvature is similar to the special Kähler manifold. It means it's hyperbolic space, which happens. Let me see. Yeah, but sometimes it happens. Okay, great. But you see, the bad things about this is the curvature of the Weil-Petersen metric, unlike the curvature of Weil-Petersen metric for Teichmüller space. For Teichmüller space, even the curvature operator is non-positive. Here, the difficulty is it is the subtraction of two positive terms. Okay, so basically the bad thing about this is the curvature is neither positive nor negative. The only thing we can show is that the curvature has, the Ricci curvature has a lower bound.
So what's the
F is called the Yukawa coupling. In our case, can be written in the following way. So it's Fijk is equal to on Z, it's omega wedge Zi Zj Ck. So this makes it holomorphic because there's no bar here. But globally, it is a section of H30 times 3 cross lambda Tz cross equals to, it's globally, it's a holomorphic section of this bundle. Okay, it has sorry. This is 2, and this is symmetry of T star C. This is times 3. So ijk means that you have T star 0 three times, but you also have omega 2 times that. Those are the sections of H30. So it's a global section of this holomorphic vector bundle. Okay. But anyway, it's locally a holomorphic function, which is similar to the special Kähler case. Okay, so let's say a little bit about the good properties and bad properties. The good properties of Will-Peterson metric, metric is, well, it's a Kähler metric, which is true for any Will-Peterson metric. And we also have its curvature formula in terms of the, we can write out its curvature explicitly. So this was done by Strominger for the modular space of Calabi-Yau threefold, and the modular space of n-fold is basically by Qinglong Wang in Taiwan, and many other good properties. So the only bad property is that the curvature is neither positive nor negative, which is very bad because basically you cannot do any differential geometry when the curvature changes sign. And we do have examples that on one modular space the curvature can either be positive and be negative. So it's hopeless to prove that you have good curvature property. So we need to change the metric. We need to study another metric. So for the modular space of Calabi-Yau threefold, such a metric can be written, can be defined in the following explicit way. So if we combine the Will-Peterson metric and its Ricci form, which is also a 1-1 form, and with this specific number, so what we can prove, we can prove is, number one, it is a Kähler metric. It's positive definite. And then it has good curvature properties in the sense that its bisectional curvature is non-positive. Its Ricci curvature and holomorphic sectional curvature are strongly negative. It's negative by a constant. Okay, so it's good, but it's still not perfect in the sense that if we have a Kähler manifold with non-negative bisectional curvature, we can say a lot about the Kähler manifold. If we have a Kähler manifold that has non-positive bisectional curvature, actually there are a lot of such manifolds. So that's the less than perfect thing. Okay, so but anyway, so this Hodge metric is to replace the original Will-Peterson metric because it has a little bit better curvature property. And we don't expect that the sectional curvature of the modular space to be non-positive. I just don't believe that, because otherwise, plus if the modular space is complete, then it's a Gadan-Hadamard manifold, which is probably not true because we have a lot of Calabi-Yau manifold and we have a lot of modular space. I don't believe all of them are that simple. So in general, we don't expect the sectional curvature to be non-positive. Okay, so as I said, we will study local theory and the semi-local or semi-global theory, which means study the property of the modular space at infinity. And there's a result I'm going to explain is the BCOV conjecture, which is so this is a mirror symmetry conjecture. On the symplectic side was settled by Zinger, and in the complex geometry side was settled by Qin and Hao Fang and myself. So this is semi-global theory. And another question in the semi-global theory is, so we want to study the incompleteness of Will-Peterson metric. So for the special Kähler manifold, the problem has completely been solved because it's always incomplete unless it's totally flat. If it's complete, it has to be flat. So that means it's always incomplete. So for for the general modular space, so it's quite difficult to do the same thing because there's a sign. I said that there's a sign difference. So this is still unsolved, and it's our preparation. Well, I'm working on that. And so there are a lot of others.
What's the issue of conjecture?
Oh, I'm going to explain. Yeah. So the global theory is actually the one I proved for special Kähler manifold was a conjecture by Fried. He conjectured there won't be any compact special Kähler manifold. So what I can prove is there's not even complete Kähler manifold, complete special Kähler manifold, other than those flat ones. So and the Gauss-Bonnet theorem, which is joined with Michael Douglas, which I will talk about it tomorrow. So these are the current result. So maybe I can take some time to define make an alternative way to define the Hodge metric. I actually never talk on this part of my result. So the Hodge metric for the modular space of Calabi-Yau threefold, we can write it out explicitly as a linear combination of the Ricci curvature of the Weil-Petersen and the Weil-Petersen. For the modular space of Calabi-Yau fourfold, we still have the same result. So that is, the Hodge metric can be represented in terms of the Ricci curvature of the Weil-Petersen and the Weil-Petersen metric. But for Calabi-Yau manifold with dimension greater than or equal to 5, we don't have explicit representation of the Hodge metric. So what we can do is we can use the classifying space method. So which this is, I prepared this basically. This is somehow related to Professor Tu's talk yesterday. So basically, we use the fact that if you have a submanifold, you have complex submanifold, then you have smaller curvature. So that's a basic property. But in our situation, it's more complicated. Is because you don't have if you have a Kähler submanifold in a Kähler manifold, then automatically you get a smaller curvature. But what if you have a Kähler submanifold in a Hermitian manifold? So it's a little bit complicated than that. So I won't explain what the classifying space is, but it is the generalization of classical period matrix for Riemann surface. So let X be a Riemann surface, then we can construct something called a period domain, and in a more intrinsic way, we can map a Riemann surface to its H10X. H10X is a moving subspace of the fixed cohomology group. So in this way, we embed the Riemann surface in terms of the Siegel upper half plane. So this idea is true even for n-dimensional case. Basically, for any manifold, we can map all its Hodge subspaces into a fixed total space. And this fixed total space is called the classifying space. So for the Riemann surface case, this is the Siegel up half plane. It has good properties. It's a symmetric space of third type, so its curvature operator is non-positive. It has, in general, for the classifying space, what we can say is, well, suppose D is the classifying space, and it has to be a homogeneous space because it's basically HPQ sitting in a HNXC. So let's assume that HPQ we just map all the Hodge matrix with P plus Q equals N. So this is a fixed space. These are the subspaces. So the set of all subspaces in a fixed space must be a homogeneous space. And with some work, we can prove, actually Griffiths proved that. So this D is always a homogeneous complex manifold. So D is always a Kähler manifold in the sense that we always have a Kähler metric on it. But D is, in general, not a homogeneous Kähler manifold. So that means you do have a Kähler metric on it, but the one which is invariant under the group action may not be Kähler. So, and well, this is trivial because any homogeneous complex manifold you can have an invariant Hermitian metric. Okay. So Griffith-Schmidt studied the classifying space, or more generally, it's called Kähler C space. So those are class of manifold which are not homogeneous Kähler, but they are complex manifold. So what they proved is one of their results is that they proved that if D is a complex manifold, and if we study the tangent bundle, the holomorphic tangent bundle of D, then with respect to the Hermitian connection, not the Levi-Civita connection, because it's not Kähler in general, then they were able to prove that the holomorphic sectional curvature of the tangent bundle is negative away from 0. So that was their result in 1969. And later, Peters was able to prove that the bisectional curvature is always non-positive. So, well, for Hermitian bundle, we can still define what bisectional curvature is. So that's what he observed. So what we can prove is the following. So for the invariant Hermitian metric on the classifying space, in general it's not Kähler, if we pull back through the Griffith period map, it has to be Kähler. And so this is interesting. And also, the metric is the Hodge metric defined before for the modular space of the Calabi-Yau threefold. It's the same thing. In Calabi-Yau threefold, we can write it out explicitly, but it also can be defined as the pullback of the natural invariant Hermitian metric to the modular space. And moreover, is that if we can pull back, so the modular space mapped to the classifying space, and with such a map, we can regard M as a submanifold of D. And if D and M were Kähler manifold, then we can say that the curvature of M should be smaller than the curvature of D, at least for the Ricci curvature. Now the situation is M is Kähler, D is not. But still, we are able to prove that the curvature on the modular space is smaller. And in addition, we have an analytic result. So when D, we can prove that this D is a Kähler C space. Basically, it is equal to the quotient of two real Lie groups, where G is a non-compact Lie group, semi-simple Lie group without compact factor, and the V is a compact subgroup. And with such a setting, we can always map it to G over K, where K is the maximum compact subgroup containing V. And if we go this way, go that way, we have a map called capital F from M to G over K. So even though that this D is always a complex manifold, in general, G over K may be a real symmetric space. So what we can prove is this map is always pluriharmonic. It's not, it cannot be holomorphic in general because this is not even a complex manifold, but we can still prove that. So this result is a consequence of these two. Okay. So, this is the, okay. So I may have some time to, so for the rest of my talk, I will introduce what the BCOV conjecture is. It's to 5:30, right? So BCOV refers to four physicists: the Bolshansky, Sekoty, Oguni, and Vafa. So in 1993 and 1994, they based on mirror symmetry, they introduced a conjecture on the mirror symmetry, which is, well, this is try to impress you. I don't really need that. So this is called the mirror map. So this is the first mirror map that was written down. So for the Calabi-Yau quintic. So nowadays there are a lot of mirror maps has been computed, but this is one of the first one. So we will only study the Calabi-Yau quintics and the dual Calabi-Yau quintics. So roughly speaking, through this mirror map, we can construct two multi-valued holomorphic functions. One is called F1A, one is called F1B. So they are defined in quite such a complicated way. Okay, so any conjecture on mirror symmetry contains two parts. One side, on one side of the mirror, it's symplectic geometry, and on the other side of the mirror, it's complex geometry. So on the symplectic side of the mirror, it's basically curve counting. So, or more precisely, we say it's the instanton counting. So let NGD be the, so for the quintic Calabi-Yau, NGD be the genus G and degree D curves, the number of those curves. And so then the simple side of conjecture is this F1A more or less is the generating function of this N1D. Well, N0D is already known to many years ago. So this is considered a known. And the N1D and the relation between N1D and this F1A is written down as conjecture A. This is the symplectic side of the story. So conjecture A was proved 3 years ago by Alex Singer in Stony Brook. So what we were interested in is the conjecture B. So we start with a compact Kähler manifold X, and let delta PQ be the Laplace on PQ forms. And by compactness, I just go through this very quickly. The Laplace has eigen, so the eigenfunctions can generate span the L2 space, so with eigenvalues of finite multiplicity, and we are able to, there's a way through the theta function regularization. There's a way to define the determinant of Laplacian even though naively the product is infinity. So we can do that. And so we are interested in the so-called BCOV torsion, which is defined to be some strange combination of the determinant of Laplacian on PQ forms. So why we define such a strange quantity is because we are able to use local index theory actually to compute it. It's not possible to compute single eigenfunction, eigenvalues, compute all of them. Like in the symmetric space, we can do that. For Calabi-Yau manifold, we are not able to. Even for a fixed determinant delta PQ, we probably don't know how to do that. But since there's a Riemann-Roch-Grothendieck index theorem, we are able to compute the combination, which is called torsion of the quantity. Okay, so this is the conjecture. Again, it's looks quite complicated. Basically, it says that this function f1b plays the central role in computing this tau. Tau is equal to some constant which related. So the right-hand side is explicit because f1b is explicit. Okay, so this is the conjecture. So we proved that conjecture, and so basically it's, you can say it's two conjectures, or they are related. There's only one conjecture because if you take the number counting, take the holomorphic curve counting, you will get a function called f1a, which is completed from symplectic geometry. By computing the tau function, if we do it in the opposite way, if we are able to compute that, we are able to find f1b. And so one is from symplectic geometry, the other is from complex geometry. But actually, it happens that these two functions are the same through the complicated mirror map. Okay, so this is we solved the mirror symmetry conjecture for genus equals 1. For genus greater than 1, then the symplectic side, the conjecture is clear. We can compute the instanton number for genus G degree D curves. For the complex geometry side, we don't even have a conjecture. So some people are working on that too. So All right. So for the rest of 15 minutes, let me just very quickly explain how to do the reduction of the problem, because everything seems to be so complicated. So the first step reduction is the following formula. So so this formula is probably well known to experts, and Haofang and I wrote in our paper. And this specific expression is in terms of the Hodge metric and the Will-Peterson metric and Hodge metric. So basically, this torsion is basically the difference between the Quillen metric and the L2 metric. And this expression is basically say the curvature of the Quillen metric is the Will-Peterson metric. And the curvature of the L2 metric happens to be the Hodge metric. And so the Hodge metric and the Will-Peterson metric is related by the log of the torsion. Okay. Here, this chi is the Euler characteristic number of the Calabi-Yau n-fold. So this is the formula. So as I said, the Will-Peterson metric is you can explicitly write it down in terms of the variation of Hodge structure. And the Hodge metric, at least for Calabi-Yau threefold, is just just more or less the curvature of the Will-Peterson metric. So it is also explicitly can be written down in terms of the variation of Hodge structure. So both sides can be written down, both omega h and omega wp can be written out explicitly. So that tells us that although this BCOB torsion is complicated, using omega h and omega wp, it can be determined up to a pluriharmonic function, because dd bar of it is completely known. Okay, so our modular space is always a quasi-projective manifold. So if tau is determined up to a plurisubharmonic function, then we only need to know the asymptotic behavior of the torsion at the singularity. Because, for example, if we assume that tau is bounded, then the solution is unique. Okay, so if we know that the torsion is log of the torsion is log of t near the singularity, then we are able to to solve this equation uniquely. Okay, so this is wrong. this cannot be correct. Sorry, but we are only studying Calabi-Yau threefold, and we assume that the H10 and the H20 are 0, so that's fine for Calabi-Yau threefold. So before we say more about this, let me explain some interesting consequence of this one. So from this identity, we will see that if n, omega h, omega, the Euler characteristic number are all in the correct sign, then the modular space cannot be compact. Well, of course, nobody believes the modular space of Calabi-Yau will be compact, but at least here is a proof. So if, let's say, we are working on Calabi-Yau threefold, so that this one is negative. And if the Euler characteristic number is positive, to say, right? So then the modular space cannot be compact, because if it's compact, then basically dd bar of a global function is equal. This is negative, this is positive. Cohomologically, they are not the same. They won't be in the same cohomology class, right? So let's assume n equals 3. So assume that Euler characteristic number is positive and n is equal to 3. So what we have is omega h plus 12 chi omega Will-Peterson is dd bar of some function, global function. Okay, so that's not possible because if you take suppose the modular space is m-dimensional, and assume that the modular space is compact, you integrate both sides, you get this is positive, this is 0. That's not possible. Okay, so using this idea, if we work a little bit harder, we can do a little bit better. Basically, we don't need to assume that Euler characteristic number is positive. We only need to assume that it's greater than negative 24. Then the modular space cannot be compact, but the modular space cannot admit any compact subvariety. because otherwise you could have integrated against this compact submanifold. Okay, so so the reason we can just modify this chi greater than from chi greater than 0 to chi greater than 24 is actually we have an inequality. The Hodge metric is at least twice as much as the Will-Peterson metric. Okay. So so I probably skipped the details of, this is the most difficult part of the proof of BCOB conjecture, and using a lot of Archilov geometry, and was done by Yoshikawa. And so basically we know that the log tau of the torsion is the asymptotic behavior of log of the BCOV torsion is this number times log of t squared and the rest. Okay, and with this asymptotic behavior plus the previous dd bar equation, so dd bar of f is known, then we are able to solve the function tau BCOV completely. Okay. Okay, I didn't realize I just finished. Maybe I don't have. So tomorrow I'm going to talk about 10 classes, but maybe I just leave it for tomorrow.
Okay. Thank you very much.